Far out in space, in the center of a seething cosmic maelstrom, extreme heat, high velocities, atoms tear, and space literally buckles. Photons fly out across the universe, energized to the limits found in nature. Billions of years later, they enter the detectors of spacecraft stationed above our atmosphere. Our ability to record them is part of a new age of high-energy astronomy and a new age of insights into nature at its most extreme. What can we learn by witnessing the violent birth of a black hole? There have been times when our understanding of the universe has reached a standstill, when our grasp of the workings of time and space, the nature of matter and energy, do not fully square with what we observe. In those times, opposing worldviews cannot be resolved. So it was in the spring of 1920 when astronomers debated the scale of the universe. The scene was the National Academy of Sciences in Washington, D.C. On one side was the astronomer Harlow Shapley, known for his groundbreaking work on the size of our galaxy and the position of the Sun within it. Shapley described the galaxy as an island universe. As large as his measurements suggested it was, it might indeed be all there is. That included mysterious fuzzy shapes known as spiral nebulae. He argued they were merely gas clouds. On the opposing side, Heber Curtis argued that some nebulae were also island universes. That idea was not new. 165 years earlier, the German philosopher Immanuel Kant described the nebulae as galaxies unto themselves. It is noted only in the Milky Way, he said, that whitish clouds are seen. Several patches of similar aspect shine with faint light here and there throughout the ether, and if the telescope is turned upon any of these, it confronts us with a tight mass of stars. It took a new generation of powerful telescopes for astronomers to finally measure the distance to those mysterious objects. Within a few years after the Great Debate, Edwin Hubble reported data showing the spiral nebulae lay far beyond the Milky Way. That led to our current understanding of a universe billions of light years across, filled with galaxies and expanding rapidly. In the years since, essential details about this dynamic universe have stubbornly resisted our inquiries. The deeper we dug into the nature of matter and energy, the more obscure they seemed to become. One of the deepest mysteries of all emerged in the 1960s. That was a time when nations were rapidly expanding and testing their nuclear arsenals. In 1963, the United States, Soviet Union, and the United Kingdom signed the Limited Test Ban Treaty, which prohibited above-ground nuclear testing. To verify compliance, the United States launched 6 pairs of satellites known as Vela, from the Spanish verb to watch over or keep vigil. They were designed to record a distinctive signal of nuclear explosions called gamma rays. Gamma rays are an ultra-high energy form of electromagnetic radiation, a term used to describe particles called photons that travel out from an energy source. The lowest energy form, radio, has a wavelength of up to 300 meters. Though we can't see them, they are produced naturally, for example, in flashes of lightning. Our eyes are tuned to capture much smaller visible wavelengths, down to 400 nanometers, or 400 billionths of a meter. Carrying even more energy, ultraviolet light has a wavelength as short as 10 nanometers. X-rays, which penetrate soft tissue in our bodies, can be as short as 1/100th of a nanometer. Gamma rays carry so much energy that their wavelength can be less than 10 picometers. That's below the diameter of an atom. They are known as ionizing radiation, which means heavy exposure can strip electrons from atoms in your body and kill you. Fortunately, gamma rays from space do not penetrate our atmosphere. Still, one theory says that a nearby gamma ray burst might have been responsible for a mass extinction 440 million years ago by destroying Earth's ozone layer and allowing in a flood of deadly ultraviolet radiation. Unlike lower energy forms of electromagnetic radiation, gamma rays are produced by the often violent decay of atomic nuclei in nuclear reactions. On the hunt for clandestine nuclear tests, on July 2, 1967, the Vela 3 and Vela 4 satellites detected a flash of gamma radiation that was unlike a nuclear weapon. As additional Vela satellites were launched, a team at Los Alamos National Lab continued to find these mysterious bursts in their data. They were able to narrow the sky positions of 16 and to rule out a terrestrial or solar origin. It would take at least 30 years to figure out what they were. A year after the launch of the Hubble Space Telescope in 1990, the 17-ton Compton Gamma Ray Observatory was set up, in part to produce a comprehensive map of gamma ray bursts. Over 1,000 detections showed the bursts were randomly spread across the sky. That led to another great debate held in 1995 to stimulate fresh thinking on the long-running mystery. Donald Lamb of the University of Chicago argued that they came from a recently discovered crop of neutron stars that had escaped into the halo of our galaxy. Bogdan Paczynski of Princeton University argued that their locations followed the general layout of galaxies and quasars. But at these distances, he conceded, the bursts would have to be the most luminous objects known in the universe. And yet a third of them disappear in less than 2 seconds. The rest die out within minutes. Were they stars flaring up within our cosmic neighborhood? Or were they something far more violent and more fundamental to the workings of time and space? In the years that followed, a revolution would sweep the field of high-energy astronomy. The Chandra X-ray Observatory was launched in 1997. It was followed by the gamma-ray satellites Integral in 2002 and Hetty-2 in 2003. The ultimate gamma-ray hunter, Swift, was sent into orbit in 2004. With ultraviolet, X-ray, and gamma-ray sensors, Swift's goal was to pinpoint as many as 100 gamma-ray bursts per year and to relay their locations down to Earth within seconds. That would allow astronomers on the ground to quickly aim their telescopes at the source to capture the afterglow. That would allow them to measure its distance and to find clues to what caused it in the first place. Those clues began to appear in early 1997. An Italian satellite called Beppo-Sachs detected a burst and relayed its location to Earth. The Hubble Space Telescope captured this image of the fading afterglow, suggesting that it came from another galaxy beyond our own. Astronomers analyzed light captured by ground telescopes and found hints that it was associated with a supernova. The association with supernovae became stronger over time. A 1998 burst coincided with this supernova. A 2003 burst with this supernova. And a 2006 burst with this supernova. But these were no ordinary explosions. Scientists were struck by the amount of energy released and by their extreme brightness. On March 19, 2008, astronomers recorded a burst that originated 7.5 billion light-years away. And yet its afterglow was bright enough to be seen with the naked eye from Earth. That confirmed a long-running suspicion that the source was a narrow and extremely powerful beam of light. What astronomers saw was actually the impact of this beam as it passed through clouds of gas, heating them up to billions of degrees and generating ultra-high energy gamma rays. Phenomena like this are not uncommon in our universe. You can find beams and high-speed jets wherever matter falls rapidly into stars, galaxies, or black holes. Few of these are known to marshal as much power as a gamma-ray burst. September 13, 2008. The Swift satellite recorded a burst with the power of 9,000 supernovae and a jet that was clocked at 99.9999% the speed of light. April 29, 2009 brought the second most distant object ever recorded. The journey of this gamma-ray burst started 13.14 billion years ago. Astronomers have begun to see these beacons as probes for understanding the chemical evolution of the cosmos, going all the way back to when stars and galaxies were just beginning to form. But how does nature produce a beacon of light that can reach across the entire breadth of the visible universe? One team of scientists has been looking for answers close to home, in a giant galaxy some 50 million light-years away, known as M87. The Event Horizon Telescope links telescopes thousands of kilometers apart into a single giant instrument. The astronomers targeted sub-millimeter radio waves because they are just the right frequency to move through dust and gas in the core of M87. That galaxy has one of the largest black holes known, at 6.6 billion solar masses. The resolution of this system was enough to collect data on a region just outside the event horizon of the black hole, the point beyond which nothing can escape its gravitational pull. The scientists were able to see down to the base of a spectacular jet that blasts continuously out of M87's core. This region is held under the spell of extreme gravity. Subject to what Albert Einstein called frame dragging, space and time are pulled along on a path that leads into the black hole. As gas, dust, stars, or planets fall into the hole, they form into a disk that spirals in with the flow of space-time. The spinning motion of this so-called accretion disk can channel some of the inflowing matter out into a pair of high-energy beams, or jets. How a jet can form was shown in a supercomputer simulation of a short gamma-ray burst. It was based on a 40-millisecond-long burst recorded by Swift on May 8, 2005. It had come from a giant galaxy 2.6 billion light-years away, filled with old stars. Scientists suspected that this was a case of two dead stars falling into a catastrophic embrace. Orbiting each other, they moved ever closer, gradually gaining speed. At the end of the line, they began tearing each other apart until they finally merged. NASA scientists simulated the final 35 thousandths of a second when a black hole forms. As the two objects move together, their mass is scrambled into a dense, hot cloud of swirling debris. On the right are magnetic fields that spin up off this cloud. Blue represents magnetic strength 1 billion times greater than that of the Sun. These fields begin to channel a cloud of plasma that surrounds the newly formed black hole. The new structure becomes steadily more organized, and the magnetic field takes on the character of a jet. Within less than a second after the black hole is born, it launches a jet of particles to a speed approaching light. A similar chain of events in the death of a large star is responsible for longer gamma-ray bursts. Stars resist gravity by generating photons that push outward on their enormous mass. But the weight of a large star's core increases from the accumulation of heavy elements produced in nuclear fusion. In time, its outer layers cannot resist the inward pull, and the star collapses. The crash produces a shock wave that races through the star and obliterates it. In the largest of these dying stars, known as collapsars or hypernovae, a black hole forms in the collapse. Matter flowing in forms a disk. Charged particles create magnetic fields that twist off this disk, sending a portion out in high-speed jets. Simulations show that the jet is powerful enough to plow its way through the star. In so doing, it may help trigger the explosion. The birth of a black hole does not simply light up the universe. It is a crucial event in the spread of heavy elements that seed the birth of new solar systems and planets. The black hole birth cries that we can now register with a fleet of high-energy telescopes are part of a wider response to gravity's convulsive power. Take the gamma-ray burst recorded by the SWIFT satellite in late March 2011. It came from a normally quiescent galaxy in the constellation Draco, 3.8 billion light-years away. Most gamma-ray bursts fade within seconds or minutes. This one lasted 4.5 hours. Scientists concluded that it could not have come from a supernova. They proposed instead that a large star had probably been thrown off track during an encounter with another star. It moved too close to a supermassive black hole in the center of the galaxy. This animation shows what happened. The black hole tore the star apart and launched a jet from matter that swirled in. The jet happened to be pointed right at Earth. We can be grateful this blast was so far away, and that we are not in the firing line of a supermassive black hole that lies in the center of our own galaxy. Astronomers have observed giant stars whipped to high speeds by this monster. Should one of these stars be thrown off its path, it could become prey. The monster will surely let distant observers know of its conquest with a blinding flash that's visible across the universe.